Hi together and welcome back to functional analysis. After some time we have just completed the section on the dual and double duals. There were 3 examples towards the end, computing dual spaces of essentially sequence spaces. Well, actually 4 examples because the first one is about Hilbert spaces. But that was sort of easy. So 3 real examples, computing dual spaces of sequence spaces, and then figuring out whether they are reflexive. Yesterday when I was editing the corresponding video, I thought I will quickly go back and make one final comment about the last example. So the last example was about LP, P different from 1 and infinity, and figuring out that its dual space is isomorphic to LQ, where Q is, well, related to P via 1 over P plus 1 over Q is equal to 1. And while we were proving this, well, strategy was to first construct the isomorphism explicitly, show that it's an isometry, and then concluding that it's actually surjective. And while we were proving the surjectivity, at some point we came to this inequality here, which is correct, but now that I read it when I was editing, I thought probably I should have explained a little bit more why the right-hand side is true, so why the yellow arrow there. Maybe I will do it with green. So once you're here on the left, then you're first going to use this, right? And then since you're looking here at the sum of non-negative terms, you might as well put here a complex modulus around. And then once you have this, then you use the right. So what you have up front is K1n, FKQ, and then less than or equal this F, and then M1n, FM, Q1 over P. Yeah, so you get this inequality. And now what you do is you move this factor here to the left, so you divide by it, and then what you will have an exponent 1 minus 1 over P, right? Yeah, but 1 minus 1 over P by definition of Q is 1 over Q, so you will have the left-hand side to the power 1 over Q, and then you exponentiate everything with the power Q, and that's why you end up here with the operator norm of F raised to the power Q. Right? That's how it works out. Okay, that is that. Now, we are off to a very exciting new section, the Baire category theorem and its consequences. This section, as I will already have said before, contains several big theorems, Banach space results, all of which play an important role in functional analysis. And to get a first feeling about what's going to happen here is we'll prove Baire category theorem. We started with realizing that actually figuring out that certain sets have non-empty interiors can be very useful in Banach space theory, or here actually even more general in normed linear space theory. We had this guy up here. So if you have a linear map, then you can check or you can test it for boundedness by figuring out if this pre-image here has a non-empty interior. And this is an if and only if test. Okay, so this we did. And now the next thing that I will do is a result that is known from the metric space module. I looked into the lecture notes, at least from last semester. So this is the Cantor theorem, sometimes Cantor intersection theorem. This is also a test that lets you check through investigating intersections of certain sets and figuring out whether they are non-empty. That test lets you figure out if the space is actually complete. Now this version that it is if and only if I actually don't need, so I wrote it here in the following way. If you have a complete metric space and a family of closed non-empty subsets which are nested, right, in this way. So the A2 is sitting in A1 and then A3 in A2. And if they're nested in such a way that they shrink down in a sense, so the diameter of each n gets smaller and smaller and smaller. And well, if they're all non-empty, closed, and they're nested in this fashion, maybe you could expect that the intersection is non-empty, and that's true. It's non-empty, and in effect, it contains only one point. Okay, this is the Cantor intersection theorem, and it is an if and only if theorem. You can check whether the metric space is complete by looking at this nested business, but that won't matter to us. So I will just quickly prove it, although it has been proven in the metric space module, but this is a super easy proof. So what you do is, since each AN is non-empty, you can pick an element in it, xn, for every n natural number. Then by the nestedness, the ones that come after xn plus 1, xn plus 2, so on and so forth, they're going to be in the an plus 1s, an plus 2, which are all sitting in the initial an, right? So in particular, then xn plus p is going to be in an for all n p in n by the imposed nesting, and thus, well, the distance between, so since we're in a metric space, I have to use this rho, n plus pth element and the initial xn, well, it can be at most the diameter of the nth a, right? So it is at most the diameter of an, and that by assumption as n goes to infinity goes to 0, right? So this shows that the sequence formed out of those points x sub n, which is a sequence of points in X, is Cauchy. Since you are in a complete metric space, it has a limit, and hence convergent. Say xn goes to x0 as n goes to infinity. Yeah, but all an are closed, so x0 must be in each an for every n, and in turn it is in the intersection of all the ans, n from, let's see, 1 to infinity. Lastly, now we have already figured out that the intersection contains at least one element. If there's two, if there is another y in that intersection of all ans, then, well, since in the intersection, then it's sitting in all a sub n's. So the distance again between that element and the previous x0 is bounded above by the diameter of an an for any n, right? And well, that diameter goes to 0. So since the left-hand side does not depend on n, we must have that those two elements are the same, right? So the intersection contains exactly 1 point, right? Okay, that is it. I would say Cantor intersection theorem here is a very intuitive thing, because although in metric spaces you should in general not use pictures to convince yourselves of facts, because in metrics the metric can behave very, very weird. But of course, the natural picture to understand Cantor intersection theorem is sort of nested concentric disks, right? So here's the biggest one, then one inside, another inside, and they all shrink down, and then, well, when they're all closed, then and non-empty, then the intersection should contain like a point like that center there, right? So that's kind of intuitive. Now, the next one on the surface is not intuitive at all, but yet it is far more important than the Cantor intersection, or that first result about being able to check whether a linear map is bounded by figuring out if this pre-image of the closed unit ball has a non-empty interior. And it is the bare category theorem. It is, again, this is more or less a result that you can discuss in a metric space module. One usually doesn't, but does it in functional analysis, and you will understand why we're interested in this result very, very soon. All right. So, but here's the statement: a countable intersection of dense open subsets of a complete metric space is dense. All right. Let me first maybe make a few comments about this before we prove it. So the assumptions here are completely essential. If you replace countable by uncountable, you can easily construct a counterexample. Density in open subsets and the completeness are also essential. The bare category theorem is just one piece of really bare category theory. One can discuss many examples attached to this. You can look into the textbooks, but we won't, because this is, I would say, more a topic in the metric space module than in functional analysis. We will only discuss this one because that's the one that will yield our results that we need in functional analysis. Now, one result that you can easily prove from this is, so you might have known, hopefully, that the closed interval 0, 1 of real numbers is uncountable, right? So now the question is how you can prove that. Well, bare category theorem gives you sort of a one-line proof, because if that thing were countable, so then you could represent it as countable union of singletons, right? And this is a countable union because I assume, this is proof by contradiction, I assume that that interval is countable, right? So you have this. Yeah, but now you just go to the complement, and this singleton here is a closed set, by the way. This is a closed set, and the metric space that I'm working with is the real line with the absolute value, okay? Because I need to be in a complete metric space after all, and that's complete. All right, so now you have this, and now the thing that you just have to do is, because you're dealing here with countable intersections, you go to the complement, right? And then there's De Morgan's laws that will turn the union into an intersection, and then that one singleton, its complement is just a real line without that one singleton, right? So yeah, but since the singleton was closed, the complement is going to be open, right? So this is open. And well, the real line removed by one point is of course dense in the real line, right? It's a union of two open intervals. That's of course dense, right? So this is open and dense. So what you have written here is a countable intersection of dense open subsets in a complete metric space, and bare category theorem tells you then the result of this, which is the complement of the closed interval, which is, by the way, of course, minus infinity 0 union 1 infinity, ought to be dense in the reals. But that's of course nonsense because it misses completely that interval from 0 to 1. Right? So that's the one-line proof why this guy here has to be uncountable using bare category theorem. There's many other fantastic results that you can pull out of bare category theory. Maybe we will discuss some in the exercises about, say, nowhere differentiable functions and as such. So, but let's see. Now let's get to the proof of this thing. So let's move this here. All right, so let's get started. Let X rho be a complete metric space, and well, that AN a family, countable family. That's why I indexed them a family. That's why I indexed them by natural numbers. A family of dense open subsets of X. Okay, now what you have to do is you have to pick an arbitrary point, and you have to show that you can creep up to it with something in the intersection of those guys, right? So let X this and epsilon be given. What does it mean to creep up? Well, we will now construct, it's rather explicit actually, this construction. So we will construct something in the intersection, because that's, after all, what we want to show is dense. We're going to construct something in the intersection that comes arbitrarily close to the given X, right? And this would then prove the density. Proving the density, that is, yeah, the density of the countable intersection. Okay, excellent. So how to do this? Well, this is a little constructive process here. So first, in the first step, so that the base case, since A1 is dense, for the fixed point x, you can, well, creep up close to it by something in A1. So we can find x1 in A1 with rho x x1 less than, epsilon over 3. As again, this cosmetic with scaling epsilons with some factors will become clear soon why this is the case. Right, so this works because of density, because all the ANs are dense in X. So you can get arbitrarily close to this starting point, small x. All right. Moreover, the ANs are open. So since AN is open, we can also squeeze in, you know, some open ball. We can find delta 1 positive with 2 delta 1 less than epsilon over 3. Okay, so that B2 delta 1, this will become clear why there's a 2 delta 1 and not delta 1 and all of this. So that this one here sits in there, right? So that's it. Okay, that's the first step. Now, having established that, you iteratively proceed in choosing. We now pick x2, delta 2, x3, delta 3, so on and so forth, inductively. So that, let's first write the properties and then explain why this is possible. Xn is an AN, and it gets sort of close to the previous x sub n minus 1. Delta n minus 1 and delta n with 2 delta n less than epsilon to the divided by 3 to the power n, so that b2 delta n xn is in the intersection of b delta n minus 1 xn minus 1. Here the notation, of course, as always, is b epsilon x naught. These are points in the metric space that are at most distance epsilon away from the center, right? So that's a ball, an open ball. Okay. So why is this possible? Well, because of density and openness. So this is possible since, well, each AN is dense. So if you have that previous point x sub n minus 1, which is a point in the space x after all, then you can choose an element x sub n in AN which gets close enough to x sub n minus 1. And then that's precisely what this condition here in green says. So let's write this out. Since AN is dense, so we can pick xn with the required property. And since xn is where in the intersection of AN and B delta n minus 1 xn minus 1. Is this clear? Well, if the green underlined stuff is true, then this precisely says that xn is at most distance delta n minus 1 away from the center xn minus 1, and that's what's written here, right? And but also xn is in AN, so that's what's written here, so it's in the intersection, right? But now careful, these are both open things, so you intersect finitely many open sets in a metric space. That intersection is going to be open, right? And that openness now allows me to choose the delta n in the way it is written there. So, and since xn, which is open, we can pick delta n as written. Alright, okay, and now what do we gain by this? Might be not so clear. Well, by construction, now it's very much like the Cantor argument. You construct here a Cauchy sequence. Rho x sub n minus 1 and xn, they are at most how much away from each other? Well, delta sub n minus 1, let's write this out, and delta sub n minus 1 by choice is at most epsilon 2 times 3 over n in the denominator, right? N minus 1, sorry, because it's delta n minus 1, so here's a minus 1. Okay, good. So, remember, a metric satisfies the triangle inequality. Now what you do is you prove you have a Cauchy sequence in estimating rho xn, xn plus k. So you're going to squeeze in all those intermediate terms, xn, xn plus 1, xn plus 2, so on and so forth, and then you can convince yourself by the estimate that we have here, you have precisely k terms that you have to squeeze in, and all of these you have to bound by 1/3 to the power n plus j, and then this epsilon over 2. All right. So now you have to convince yourself that this thing here is finite, but that's easy because you can sort of estimate it from above by a geometric series. That's why you have those thirds floating around. So what you get here after a little calculus is 3 epsilon over 4, 1 over 3 to the power n, right? And that, of course, as n goes to infinity, goes to 0. Hence, the sequence formed by the xn's is Cauchy in a complete metric space, and so convergent. That's why I said this part here right now is very similar to Cantor. That's why I discussed it up front, as n tends to infinity, say. Okay, and now all that remains to show is that this limit is really, the guy, well, it's already denoted in that fashion, and now we have to see that this guy gets arbitrarily close to the starting point x, and that it sits in the intersections of all the an's, and then we would be done, right? Okay, so let's do this also by construction. And now you realize why I had to do this 2n business, 2 delta n business, because obviously you have this inclusion here. So a disk of half the radius with the same center is in the disk of, the original radius with the same center. And in particular, you can now put the closure on the left-hand side, and it will be properly contained in what's written on the right-hand side. That's why the surgery about 2 times delta n. This we already know, right? Also by construction we have this, and so these xn's, xn plus 1 and all subsequent ones, they are not just in the B2 delta n, but actually in the closed one with half the radius. So you have this, okay? So and that's why they are contained in closed sets, and then very much like in Cantor, you get that the limit is also in the closure B delta n xn, closure thereof, which sits in an for all natural numbers. Okay, hence x infinity is in the intersection of all the an's, okay, and by construction we have that element gets close to what we want to be, namely the starting point x. So by triangle inequality can, for instance, insert the first one, can insert any of the other ones, wouldn't matter. Now the first one by construction was distance epsilon over 3 away. So 3 less than or equal. And then for the other one, again, you do the triangle inequality trick and you insert, well, now infinitely many terms. So j1 infinity, 1/3 to the power j. And that is again a convergent thing. And actually you can compute it. You will figure out this is strictly less than epsilon. Okay, and that's it. This completes the proof. Because you have shown that this limit element x sub infinity, which is in the intersection of all the ANs, gets arbitrarily close to the starting element sub x, and so the countable intersection of dense open subsets of a complete metric space is dense. Okay, that's it. The Baire category theorem, as I said now many times, is very nice. There's a whole lot of theory around it. Actually, for our purposes, we only need from that theory the following short corollary. Let X be a complete metric space and Cn a countable family of closed sets that, well, sort of add up in a sense, well, in the union sense, to the whole space. Okay? Then some Cn has a non-empty interior. So now we get back to the non-empty interiors. This was what we discussed in the very first result in this section. Okay? This here. So this is a one-line corollary to the Baire category theorem. Baire category theorem deals with countable union of open sets. So whenever you see countable closed sets, you go to the complements and derive this stuff from Baire category theorem. I will do this in the next video, and then we will pull out the first consequence, the first big result in functional analysis. Baire category theorem again is big, but it's more of a metric space result. But then we will pull out the first very, very important functional analysis theorem in this section. Okay, see you soon.